Here's the big news for Chapter 7. You can use your calculator for the entire test. If you can correctly set up those integrals, then I'm happy you've learned what you were supposed to learn from Chapter 7, and you do not have to waste your time on that arithmetic. So from here on out, you have my blessing to use the calculator. And that even includes, if you need to use Desmos to graph something in terms of y that you can't do on your TI 83 or 84, you can go for that. Because the point of this test is to be able to set up those integrals. And the first thing you have to be able to do with those integrals to be able to set them up, you gotta draw a picture. So again, if you don't know what the graphs look like, go graph them, either on your calculator or on Desmos, because you've got to have an accurate picture. And so the first thing you had to be able to do is you had to be able to find the area between two curves. And the biggest thing I would say to watch out for on those is make sure that your top function doesn't change, right? Let's say I wanted to find the area between these two curves here. The enclosed space I can see is this region and this region. But what I'll notice is that this function that was on top becomes the bottom function at this next region, right? So look at your graph, examine your graph carefully. What you'll have to do on this one is you'll have to do two separate integrals. Let's say this was A, B, and C. You'll have to do the integral from A to B plus the integral from B to C, where your top function is going to change in the middle of that problem. Okay? But these aren't bad at all. So you've got the integral from A to B of whatever your top function is minus your bottom function. Area between two curves, not too bad. Not too bad. They get a lot more exciting when we start taking regions and revolving them about an axis. Solids of revolution. Right? Let's say that I had this function, f of x, and from A to B, I've got this region here, and we're told that we are revolving that region around the x-axis. So I know that I'm going to set up my integral. This is going to be pi times the integral from A to B, and A and B may not be specified. You may have to read those off of the graph. Anyway, this is going to be the integral from A to B of the radius of the disk squared. And this is where it always helps me to draw that representative slice here. And I can see that the radius is just equal to the function, right? So I'm going to take that function and square it and integrate with respect to x. Now I can tell you this, the most common mistake, now that you're allowed to use your calculator, the most common mistake is going to be forgetting your pi, right? So don't forget to multiply your integral by pi. You're going to get some decimal, right? But all your answer choices are going to be proper fractions, usually in terms of pi. And so all you have to do is go check all your answer choices, type each one in, get the decimal, pick the decimal that matches what your calculator spit out for you. If we have that same region and we wanted to this time revolve it around the y-axis, let's say I'm going to cut that off here at, x equals 2. So I'm just going to take this region and multiply it about the y-axis. Well, I've got two problems now. First of all, I'm in terms of y. So my function, I'm going to have to solve that for x so that I have a function of y instead. Second problem I have is that I've introduced a hole. There's a hole here. So when I draw my representative slice, I see that I'm going to have a big radius, r of y, and a little radius, little r of x. That representative slice always helps me because I'm looking at these endpoints right here, and I'm going, how can I calculate that endpoint? This one's easy. It's the same the whole way. It's just x equals 2, right? That's my big radius, x equals 2. This little radius right here changes with that function. I can see that's the function in terms of y. Okay? The other thing you have to be careful of was when you integrate with respect to y, is look at your limits of integration, right? That's going to be on your y-axis. So when I get ready to integrate this is the pi times the integral from a to b, and again, those are y-coordinates now, of the big radius squared minus the little radius squared. And those got really messy and really tedious, but it should be a cakewalk now that you've got your calculator to use as a tool. Next thing that we looked at were volumes with known cross sections, And so the way those always work when you're talking about something with a known cross-section is first you've got a graph that gives you the base. So this is like the top view. You're looking down on your shape, and this is the shape that the base is going to be. Okay? And then it tells you what the cross-sections are perpendicular to that base. And so let's say this tells you, this makes squares perpendicular to the region enclosed by the graph of blah, blah, blah. Let's say it tells us that those are squares. So if I were now to look at from the side, all my cross-sections on the side would be squares. And so that cross-section has some area, and what you're doing this time is you're integrating from A to B all of those areas. Okay? And this is where it gets very specific to the shape, whatever that cross-section is. So when I draw my representative slice here, that's giving me the base of whatever my shape is. So in this particular case, this cross-section is given by whatever the function is, and then that is the side of a square. The area of that square is side squared, so that's f of x, and then I'm going to square that. And so that's what's going to go in for my area here. Just keep in mind, what I want you to do is I don't want you to mix these up with a solid revolution. There's no pi, and it's not necessarily squared. What if this had been triangles? If this had been triangles, then this right here is the base. That area is just 1/2 base times height. I'd have to have some other information to get the height, but the point is that nothing in there is squared, right? So just be aware that pi and the function squared, that's always tied to a solid of revolution. For these areas with known cross sections, those are specific to the shape. So this one happened to be squared because that was the formula for the area of that shape. Okay. Last thing that we did were those impossible integrals, and the point of that is just making sure you know the second fundamental theorem of calculus. If you integrate f of x, you get the integral, so we're going to use capital F for that, of the upper limit minus the integral evaluated at the lower limit. And so the way these problems work is they expect you to use your calculator here. And that's when we unleashed this beast of being able to use your calculator. They expect you to get a decimal here, and then one of these is going to be given, and then you solve for the other. Just by simple subtraction, right? That's how those quote-unquote impossible integrals work, is you'll use your calculator to solve the actual integral, get the decimal, and then one of these is going to be given, and you solve for the other one. The only thing I would watch out for is sometimes they try to trick you with the notation, right? If I had y prime, we know that's a derivative. Well, if I integrate a derivative, I should end up with the original function. So you'd integrate that minus y of a. So just don't let notation fool you. If you integrate f of x, they typically use a capital F. And then if you integrated f prime, you would just get the original function back. If you integrated, I don't know why they would do this to you, but if you integrated f double prime of x, you'd end up with f prime of x. Those are the ways they can make it a little trickier because they are such simple problems to actually work out. I think this is the hardest test in terms of setting up the problems, but you don't have to waste your time on the arithmetic. So you should have time on this test to draw good pictures, make sure you're setting things up correctly.